Hello, I'm Ryan Baker, and this is Big Day in Education. Today we're going to start our discussion of classifiers. You may remember from previous classes that in prediction, we develop a model which can infer a single aspect of the data, the predicted variable, from some combination of other aspects of the data, the predictor variables. We sometimes use this to predict the future, and we sometimes use it to make inferences about the present. In this class, we're going to talk about classification, which is a type of prediction modeling. Again, like any type of prediction, there's something you want to predict, the label. And in classification, the thing you want to predict is categorical. The answer is one of a set of categories, not a number. It could actually be binary, 0, 1. That still gets treated as categorical data for this purpose. So for example, it could be correct or wrong, which is actually the special case of latent knowledge estimation. It could be, did the student make a help request, make a worked example request, or attempt to solve the problem with no help? It could be, will the student drop out or not? Or it could be, will the student enroll in MOOC A, B, C, D, E, F, or G? You may say quickly, where do these labels come from? And they can come from a lot of places. Student in-software performance, was the student correct or wrong? School records, test data, survey data, field observations or video coding data, text replays, that's pretty prints of log files of student interaction with software. Didith Rodrigo's EDM Workbench is a good tool if you want to learn more about that. In classification, associated with each label are a set of features, the predictor variables, which maybe you can use to predict the label, the predicted variable. So in this example, maybe you want to predict if the student is right or wrong, and you can do that from the PNO, the probability the student knows the skill, the time taken for the action, the total number of student actions, and maybe the skill too. The basic idea of a classifier is to determine which features, in which combination, can predict the categorical label. There are hundreds of classification algorithms, and a good data mining package will have a lot of different implementations. Data mining packages like RapidMiner, SAS Enterprise Miner, Weka, or Keel will have a lot of different classification algorithms you can try. You might not actually want to try several hundred, though, for various reasons we'll get into later in the class. One issue is domain specificity. You may have heard algorithm X is the best algorithm out there. Well, specific algorithms work better for specific domains and problems. We often have hunches for why that is, but it's more in the realm of lore than really engineering. We don't really know why certain algorithms are so much better in specific domains. Some algorithms I find useful in educational data include step regression, logistic regression, J48 or C4.5 decision trees, JRIP decision rules, and K-star instance-based classifiers. We'll talk about all of these at some point in the class. There are a bunch of other ones, and we'll talk about a few of the other ones as well. Let's start with step regression. First thing, step regression is not stepwise regression. They have similar names, they're not the same thing. Step regression is used for binary classification, 0, 1. Will the student drop out or not? In step regression, we fit a linear regression function, as we discussed in the previous class, with an arbitrary cutoff. So what we do is we select variables, also called parameters, we assign a weight to each variable, we compute a numerical value from adding all those together, and then we take all the values below 0.5 and we treat them as if they're 0. And all values greater than or equal to 0.5 are treated as 1. So let's give an example. Let's say y equals 0.5a plus 0.7b minus 0.2c plus 0.4d plus 0.3, and our cutoff is 0.5. That's the most common cutoff. So let's say the values of a, b, c, and d are 1. Well, in that case, 0.5 times 1 is 0.5, plus 0.7 minus 0.2 plus 0.4 plus 0.3. Is that greater or less than 0.5? Well, it's 1.7, so it's greater than 0.5, so it's 1. What if they're all 0? Well, 0, 0, 0, 0 plus 0.3 is less than 0.5, so we get 0. And negative 1, negative 1, 1, 3. Pause the video for a second. Try it out. You'll see that the answer is below 0.5, so it's 0. Step regression. Should you use it? Well, I like it. Some statisticians don't like step regression due to the lack of a closed form expression, which makes it hard to compute things like standard errors. But it often does better in data mining because it's very conservative and it doesn't tend to overfit. Now let's talk about logistic regression. Logistic regression is another algorithm for binary classification. Will the student drop out or not? Given a specific set of values of predictor variables, it fits a logistic function of data to find out the frequency or odds of a specific value of the dependent variable. And here's a logistic function. They can actually be steeper or less steep depending on some details. And what you do is you take a function m, which is a constant plus a set of variables and weights, and you compute p of m is equal to 1 over 1 plus e to the negative m. So let's try that out. Let's say we have the function m equals 0.2a plus 0.3b plus 0.4c. So if they're all 0, then m is going to be 0, and consequently p of m is going to be 1 plus e to the 0, which, if you work it out, turns out to be 0.5. Try it in Excel. If they're all 1, then m will be 1, and p to the m will be 0.73 again. Try it out in Excel. And if they're all -1, m is -1, you'll notice that before, when it was 1, it was 0.73, 0.23 above 0.5. Now it's 0.23 below 0.5. And so on. For 2, it's 0.88. For 3, it's 0.95. And if they're all 50, it's just so close to 1 as to be basically 1. Logistic regression is relatively conservative thanks to its simple functional form, and I'll explain this in more detail later in the course. It's good for, among other things, cases where changes in the value of the predictor variable have a very predictable effect on the probability of the predicted variable. So for example, in this case, 0.2a plus 0.3b plus 0.5c, higher a always leads to higher probability. But there are some data sets where this is not always true, where things aren't so neatly linear, or logistic, I guess. What about interaction effects in particular? A is bad, B is bad, A plus B, that's good. And there are some examples in the real world. Ineffective educational software is bad. And going off task in class, ignoring what you're supposed to be doing is bad. But, ineffective educational software plus off-task behavior might actually be good if the student is spending that off-task behavior doing something more worthwhile. Logistic and step regression are good when interactions aren't particularly common. You can actually give them interaction effects through automated feature distillation, and we'll discuss this later in the class. But it's not really particularly optimal for this. This is not really the best thing you want to be doing with logistic or step regression. Instead, you may want to use algorithms like decision trees, which are kind of more explicitly dealing with interaction effects. Here's an example of a decision tree. If knowledge is less than 0.5 and time is less than 6 seconds, so we're going down the left side of this, then the student's right. But if knowledge is less than 0.5 and time is greater than or equal to 6 seconds, then the student's wrong. The other branch, with a different set of variables, is that if knowledge is greater than or equal to 0.5 and total actions is less than 4, then the student's right. But if it's greater than or equal to 4, then the student is wrong. So if we have a student with knowledge of 0.544, we're going to go down the right side to total actions. Total actions is 1, so it's less than 4, so the student is right. So there are a lot of decision tree algorithms. I usually use J48, which is an open source reimplementation in Weka and RapidMiner through the Weka extension plugin of Ross Quinlan's C4.5 algorithm. It's one of the classic ones. It can handle both numerical and categorical predictor variables, which is kind of nice. It predicts a categorical variable, but you can predict that with numerical or categorical. And it tries to find an optimal split in the numerical variables. It repeatedly looks for the variable which best splits the data in terms of the predictive power for each variable. And it later prunes out branches in the tree that turn out just not to be all that good after all. And you note that different branches can have different features, like in the example I showed you a minute ago. It can also be adjusted to split based on more or less evidence, and to prune to throw out branches based on more or less predictive power. It's relatively conservative. You'll note this theme. I like algorithms that are relatively conservative. We'll talk about why later in the class. Thanks especially to the pruning step. It's good when the data has natural splits, like you see in this graph here where there's kind of a bimodal, and so there's a natural split in the data. It's also good when multi-level interactions are common. And it's good when the same construct can be arrived at in multiple ways. For example, let's say that a student is likely to drop out of college either when he starts assignments early, it's a hard-working student, but he lacks the prerequisites to success, or when he starts assignments the day they're due. You can imagine two very different students that both drop out of college but show these patterns.
So what variables should you use?
In one sense, the entire point of data mining is to figure out what variables matter. But some variables have more construct validity or theoretical justification than others. And using those variables generally leads to models that are more likely to generalize to new contexts. We'll talk more about this issue in a future lecture. More urgently, some variables are going to make your model general only to the dataset where the model was trained. And these kind of variables should not be included in your model. They're typically the variables you actually want to test generalizability across during cross-validation. These are typically the variables that you want to test generalizability across during cross-validation. We'll talk more about this theme in a future lecture. But to give a quick example, your model of student off-task behavior should not depend on what student you have. It shouldn't say, if the student's Bob and the time is more than 80 seconds, then do this. Because this model is not going to be useful when Bob's no longer part of your dataset and you're looking at totally new students. Also, your model of student off-task behavior shouldn't depend on what college the student's in. So your model shouldn't say, if the school is the University of Pennsylvania and the time is more than 80 seconds then. Because this model is not going to be useful when you're looking at data from new colleges or new schools. Instead, you want to make sure that the model works across the colleges and schools that you have. Now note, in modern statistics, you often need to explicitly include these types of variables in models to conduct valid statistical testing. This is the difference between classification and statistical modeling, and we'll discuss it more in future lectures. Now in later lectures, we're going to talk about more classification algorithms. We're going to talk about goodness metrics for comparing classifiers, validating classifiers for generalizability, and what it means for a classifier to be conservative. So thank you very much. The next lecture, building regressors and classifiers in RapidMiner.